So the dimensionless ratio of the forces show that electric force are enormously stronger than gravitational forces. Till last year you have seen that there are four type of forces. One is electromagnetic or electrostatic forces. Both are same, electromagnetic. In the starting of this chapter itself we have seen that there is a unification between electricity and magnetism. Another type of forces are strong forces, weak forces, and last type of forces are gravitational forces. Okay, so now the second part of this question is that first we have to calculate, then we will calculate the acceleration on proton as well as electron. So let us calculate this. The electric force F exerted by a proton on an electron is same in magnitude. As you know that both the forces should be same in magnitude, only opposite in direction. So this time we have taken F as its magnitude in mod. So 1 upon 4 pi epsilon naught E square from the first equation. So E square upon distance R square. So now let us take what is this, let us calculate this. R square has already been given to us as 1 angstrom in this question. So once we put these number 1, 4 pi epsilon naught, you know, 8.85 into 10 to power minus 12, E square 1.6 into 10 to power minus 19 square of that, and what is radius? 10 to power minus 10 square of that. So you get this number 8.987, you can also say 9 into 10 to power 9 meter square per coulomb square. Okay, so this is a huge number. So this is a huge number. This number 1 upon 4 pi epsilon naught that you have already seen. Now E square 1.6 into 10 to power minus 19, this is coulomb square, and radius 10 to power minus 10 square. When you calculate this thing, this comes out at 2.3 into 10 to power minus 8 Newton. 2.3 into 10 to power minus 8 Newton. Again, this force does not look very huge because it is minus 8, but when you take the size of electron and proton into consideration and the distance between them, this force is again very large. This does not look very large because you are not considering the size of protons and electrons, but when you consider that, this force is again quite large. Using Newton's second law, F is equal to ma, you know both how you can calculate acceleration out of this force. The acceleration that an electron will undergo, you just take this acceleration A is equal to this force upon mass, and this comes out 2.5 into 10 to power 22 meter per second square. So now you can understand that how high this force is when you put the mass of electron. Again, for proton, force remains the same, only direction reverses. That will not change the magnitude, or that will not change the magnitude of this force, only the direction will change, and divided by the mass of proton. This time mass of proton, last time we have taken the mass of electron, this time mass of proton. So this comes out at 1.4 into 10 to power 19 meter per second square. This is again huge. Can you think of an acceleration of 10 to power 19? How high this acceleration is? Comparing with this value to acceleration due to gravity, you compare what is the acceleration due to gravity is simply 9.8 meter per second square. We can conclude that effect of gravitational field is negligible on the motion of electron. So if you put the effect of gravity on this, that is almost negligible, and it undergoes very large acceleration under the action of Coulomb force due to proton. The value for acceleration of proton we have calculated. So both are very large, and effect of gravity on their acceleration is almost nil, can be neglected. So if you subtract 9.8 out of this or add 9.8 to this, that will make no effect. Very similar to example that I always give in the class, that if you add one bucket of water or if you take one bucket water out of the sea, that will not make any difference. Very similar to that. So now another example. The example is a charged metallic sphere A. Here it is the charged metallic sphere A is suspended by a nylon thread. This is suspended so it can move freely. Suppose if we bring something closer to this, so it can attract. Otherwise, if the charge is quite low, even though there are some forces like that, attractive or repulsive forces, but due to friction those will not play their role. So that's why we are suspending this with a nylon thread, so even a very small motion can be detected. A charged metallic sphere A is suspended by a nylon thread. Another charged metallic sphere B held by an insulating handle. So why insulating handle? Otherwise the charge will be gone through our hand to earth if it is not insulating. So insulating handle is brought close to A such that the distance between their centers is 10 centimeters. So this point and this point is 10 centimeter apart. Okay, both of them are 10 centimeter apart as shown in figure. This the resulting repulsion of A, this is definitely, if both are positive then there must be a repulsion. This is noted, for example, by shining a beam of light and measuring the deflection of its shadow on the screen. Okay, so a beam of light is measuring the shadow on the screen, then how it is changing or how it is moving. Spheres A and B are touched by uncharged spheres C and D respectively. See, now we have made the things complicated. These are touched by spheres C and D, and as you know that charge will be equally distributed. So here 1, 2, 3, 4 positive charges, 1 and 2 are on A, 2 are on C. That should be uniformly distributed. As well as if there are 2 positive charges on B, so one is on B, another one is on D. So these are additive properties as well as equivalent distribution properties. So now let us understand. So C and D respectively as shown in figure 17b. This is shown. Okay. C and D are then removed. This C and D are removed. Once touched, after that these are removed. So okay, so brought closer to this as shown in this, then C and D are removed and B is brought closer. Now B is what we are doing with this B. We are bringing B closer to a distance of 5 centimeters rather than distance of 10 centimeter. Now B is 5 centimeter apart from their center as shown in 17c, third figure. Okay, third figure. Now the distance is 5 centimeter. What is expected repulsion of A on the basis of Coulomb's law? Spheres A and C and B and D have identical sizes. We will discuss why they are taking identical sizes of A and C and B and D. So what is expected result of force or repulsion after doing this activity? Ignore the sizes of A and B in comparison to separation between their center. So again we are ignoring the size of this A and B, so we can consider them as point particle, as we have discussed in Coulomb's law that particles should be point particles in Coulomb's law. So distance first is 10, then touched, and then distance is reduced.